All right, here we're in section 4.2. We're looking at how to find the inverse of a function as well as some properties associated with inverses, okay? So the inverse of a function is defined to be the correspondence from the range of the original function f back to the domain of f, okay? And if you're trying to find the inverse of f, then its inverse would be represented with this notation. It looks like f raised to the negative first power, but it is read as the inverse of f, okay, or f inverse. So let's say f of x has the following 5 points associated with it. By this definition, all we're really stating is that the inverse is going to be found by switching the x and the y coordinates from the original points in f, okay? So we'd end up with 3, -2, -1, 3, 0, 2, 5, 4, -6, 2. Okay, pretty simple. Let's say you want to graph the inverse of a function. Okay, well, all you need to do is follow this rule of switching the x and the y values, and you can plot new points to give the graph of the inverse function. Okay, so kind of to verify this, let's say we're working with the cubic function and the cube root function. Those are in fact inverses of each other. Let's prove it. So y equals x cubed has points of 0, 0, 1, 1, 2, 8, -1, -1, -2, -8, right? Those are the critical points. And then if I were to switch their coordinates, well, these 3 points would stay the same. 2, 8 would move to 8, 2, -2, 8, -2, -8 would move to -8, -2. And that graph should look familiar too. It is, in fact, our cube root function. Okay. Now, I want you to notice that those two curves are symmetric across this line, which is the line y equals x, where any point on that line, the x and the y coordinate are the same. Okay. So we have this theorem that says the graph of a function f and its inverse are always going to be symmetric with respect to this line, y equals x. It's a really good way to visually determine whether two curves are in fact inverses of each other when given their graphs. Okay. So now I want to ask the question, is the inverse of a function always a function? Okay. To do so, we're going to use this investigation. You can open it up with me. All right, so we're going to scroll down, and there's some directions below the applet that we're going to follow here. So step 1 says to choose the default to natural domain of f option. Okay, so we're going to check that box, and basically what that means is when that box is checked, whatever function you are working with, it's going to show the entire graph over all of its domain values. Okay, in this case, the domain for this function is all real numbers. All right. Step 2, I'm going to ignore. I'm going to leave it as f of x equals 0.2x squared. Now, step 3, show the inverse relation. Okay, so it graphs the inverse in green here. Notice the red curve is a function, the original f of x, but its inverse is not a function. The inverse doesn't pass the vertical line test. Okay, they are in fact inverses. Notice they are reflecting across or symmetric across y equals x. Okay, so now we want to look at, well, how can I make it so that the inverse of this function will in fact be a function itself? Okay, so now we're on step 5. It says to uncheck the default to natural domain of f option. Okay, so I uncheck that, and now what it does is it gives me some sliders that I can use to play around with the domain of f of x. Okay, so right now you're seeing f of x only for x values from -4 to 3, okay? If I click show inverse relation, I still have the same issue that it's not a function, okay? So I can play around with these sliders until I get the inverse to in fact be a function itself, okay? So lots of different ways you can do this, but I'm going to restrict it so that the domain is only showing to be from -4 to around 0, okay? Once I adjust the domain to that, notice the green curve is in fact a function, okay? And I hope what you're noticing is that the only way the inverse is going to be a function is if the original function is a one-to-one function. It's been a while since we talked about one-to-one functions, but recall those are functions that pass both the vertical and horizontal line tests. It means there's no repeat x values or y values, okay? So right now red is one-to-one, which means green is one-to-one as well. If I make red not one-to-one, like so, green's not going to be a function, okay? So let's put this in our notes. We see the inverse will only be a function if the original function is one-to-one. Okay, so assuming we are working with a one-to-one function f, then four properties between that function and its inverse would be that the domain of f equals the range of the inverse, and then the range of f equals the domain of the inverse. And then a couple other properties associated with the composition of the two functions. F composed of the inverse of f will equal x, and the inverse of f composed of f will also equal x. Okay, so let's verify those last two properties, properties 3 and 4, with the cubic and cube root functions. Okay, if I were to find f composed of the inverse of f, that would simply mean to find the cube root of x cubed, which we know is going to simplify to x, right? And then the inverse of f evaluated with f of x would be the cube root of x cubed, which is also x. So there's just proof again that based on properties 3 and 4 that cubic and cube root functions are inverses of one another. Okay. All right, now, how do I find the inverse equation of a one-to-one function? Okay, so this would be in the case of a continuous function that has an infinite amount of points to it. I can't possibly list out an infinite amount of points for the inverse, right, by switching x and y. So I need an equation to represent it, okay? So here I have a linear function, f of x equals 2x plus 6. All lines are one-to-one, right? So I know that the inverse is going to be a function as well here. So to find the equation for the inverse, I'm first going to think of f of x as y. I'm going to treat this as y equals 2x plus 6. And then I'm simply going to switch the position of x and y. All right, so right here is an equation to represent the inverse function. The problem with it as is, though, is I have x alone when really we are used to y being alone. We like our equations to have y as the dependent variable and x as the independent variable. So I'm going to take this equation and solve it for y. Two steps to do so. I'm just going to subtract 6 from both sides. It's going to lead me to x minus 6 equals 2y. Then I'm going to divide both sides by 2. And that will take me to y equals 1/2 x minus 3. And since this was a one-to-one function originally, I know that this resulting inverse is also a function, So I'm going to use function notation. Okay, there you have it. All right. Second example of how to find an inverse equation. Here I want to find the inverse of h of x equals the square root of x minus 3. So same process as the previous example. I'm going to treat h of x like a y, and then I'm going to switch x and y, and now solve back for y, which is going to require me to square both sides. X squared is equal to y minus 3. Then you're of course going to add 3, and you're going to end up with y equals x squared plus 3. Okay. Now, so I think it's no surprise that a square root function, it's going to have an inverse that's a squared function, right? But think about this. Y equals x squared plus 3. Normally that's a parabola, right? Well, parabolas, they aren't functions in themselves, okay? So that means that in order for this to be considered a function, I'm not looking at the entire graph of y equals x squared plus 3. Okay, so I'm gonna use function notation here, and I now want to consider what does the domain of this need to be if I'm thinking of it as a function. Okay, well, it all goes back to what's the range of the original function h of x. Okay, kind of visualize this. Hx it's just going to be your square root function, your parent square root function shifted 3 units to the right. So this graph's doing, something like this. Okay. The range of that is any number greater than or equal to 0. That's going to turn out to be the domain of the inverse function. So we're going to say that x has to be greater than or equal to 0, which means we're really only looking at the right side of the parabola. Okay, we're only looking at this side if we're trying to treat it as a function. Okay, and notice once again, if we think of it like that, then we have the symmetry between the two at y equals x.